The title of the lecture today is Landing on a Planet at 600 miles an hour. In fact, it's more like 700, and I won't actually be landing on any planets, but you'll get the general gist, I think, of things as we go on. So we're talking about the exploration of the solar system and technologies associated with that, and one particular technology which we've brought on at UCL and MSSL. So the solar system is a big place. That all the things in it are more or less the same shape, as you'll notice. They're a long way apart. To travel there is very difficult. We haven't been there for a long time. To send things there to do measurements for us is also difficult, but not quite as bad. And that's the sort of thing that we're engaged in the exploration of the solar system with remote instrumentation. Of course, to do this sort of thing, you need spacecraft. This is Cassini, a spacecraft currently orbiting Saturn. We've got a bit on board. I can't really point it out to you, but there's an MSSL instrument on board at the moment, orbiting Saturn. We've got other instruments orbiting Venus and Mars at the moment, so we get around the solar system as best we can. These bits of kit, though, are not inexpensive. I have to say that's the top end of the spectrum, but that's $3 billion worth of kit. So we have to play the long game here. What we call the development of technology is a long game that can take 15, 20 years from concept to actual deployment, because it is an enormously competitive era, and you can't afford to waste large sums of money like this. So the technology I'm going to be talking about is a technology which is in its early stages. It hasn't got to the planets yet, but you'll see where we are. One of the reasons, and there are many reasons why we are interested in the exploration of the planets, but one of the primary reasons for exploring the planets is to get to grips with this thing that we call life. Okay, and there's not much text on the screen that I'll show you today. It's mostly pictures, but here's some questions that we are interested in. One interesting question is, what are the conditions necessary for supporting life? And we find more and more that those conditions are more and more extreme, which means that more and more places in the solar system have the potential to support life. We can ask where those conditions exist, and we can tell quite a lot from looking at the solar system through telescopes and from spacecraft in Earth orbit, etc. But to really get to grips with the sort of ground truth, you've really got to put something on the surface, or at least orbit the planet or the moon that you're interested in. Ideally on the surface, where you can make in situ measurements of the surface or even below the surface. Then we can ask questions like, if we understood what those conditions were, how common are they in the universe? And that's a sort of another story, really. But it leads on to two questions. One is there life elsewhere in the universe? And I hope to sort of half answer that in the last slide. And the final question that everyone asks is, are we alone in the universe? And that really says, is there sentient life elsewhere in the universe? And to be honest, that is an enormously difficult question to answer. It's very difficult to know what the probability of life turning into sentient life is at the moment. So what I'm interested in when I talk about life here, what I'm interested in is really just complex chemistry. We call it life, but it's very, very complex, sophisticated chemistry. And we generally believe that that sort of thing is going to happen whenever the conditions are right, and you wait a couple of billion years. So if you can find those conditions that have been around for a long time, when we sort of half expect to find life there. The Earth is a very unusual place as far as we can tell. It's certainly unusual in the solar system because it's got all this blue and wispy white stuff around it, which is evidence of the water. And we think that life basically requires water to evolve, not necessarily to begin, but to evolve. And so we're interested in the circumstances of the Earth being as it is. That's a very interesting thing. To understand why the Earth is as it is, we have to understand how the Earth formed and why the Earth formed, and what were the sort of circumstances around the solar system 4 and a bit billion years ago when the Earth formed. And one of the things that happened around that time, it seems, was there was a collision. There's an artist's impression. There was no photographs of it taken at the time, as far as we know. But there's an artist's impression of the collision. It was something about the size of Mars colliding with the Earth. One can imagine that such a collision is going to be quite traumatic. The outcome of that collision was the creation of the Moon. At a distance quite close to the Earth, perhaps not quite that close, but quite close to the Earth. The Moon has drifted out in time. The presence of the Moon in our environment has had profound implications to do with the existence of life on Earth. Some people argue that without a moon of that type, life wouldn't have evolved. And that's, or at least would have taken a lot longer to develop into sort of sophisticated creatures like ourselves. So we're interested in what was going on in the inner solar system at 4 billion years ago that led to some stable planets which could maintain an environment for billions of years which would create life. Now, we've been around the solar system a little bit, and so these are the objects in the solar system that we've, if you like, we've touched the surface of, okay, in one way or another. The Moon, of course, Venus, things have been landed on the surface of Venus by the Russians many years ago. Mars, lots of things on Mars. There's things rolling around. Well, there's one thing driving around Mars as we speak. We dropped a probe into the atmosphere of Jupiter. Of course, when I say we, I mean humanity. It was Americans that did that. We've landed on this asteroid Itokawa and possibly brought some samples back. The Japanese did that. We've certainly landed on Eros. We've dropped a probe through the atmosphere of Titan out there around Saturn, and we've had an impactor on this comet Tempel. So we've started to sample. Now, there are a lot of objects out there that we could look at. There are the planets, and some of the planets have nice solid surfaces, which would be interesting to us. The big planets without the solid surface is a bit more tricky, but all those big planets like Jupiter and Saturn, those two, have dozens of moons. They have like 60-odd moons each. And so these moons actually are probably the most interesting things in the solar system. There's something like 170 moons in the solar system, all of which are just dying to be investigated by us. So we've got plenty of opportunity out there. And the strange thing about them is they all seem to be different. There's just such a variety of geophysical circumstances. Now, one way to land on the moon, one way to sample a foreign body is to what we call a soft landing. Soft landing is like the classical thing where you see it in the science fiction movies. Something comes gently down and lands a few meters per second onto the surface, and it's very good. The first soft landing on any object was Lunar 9 on the 3rd of February 1966, a Russian probe. The Russians, of course, were the first to everything up until Apollo. Before Apollo, everything was American first. After Apollo, everything was a US first, pretty much. And so in '66, they landed something on Mars. It's not an easy thing to do. And that's one of the messages in here, is that soft landings are not an easy thing to achieve. You know, it's an airless body, so you haven't got to worry about the wind, but it's still an unknown terrain. It's a very long way from home. It's got to sort itself out. In fact, these little images across the bottom, I always forget the number, but I think it's about 10, might be 11, 3, 6, yeah, it was the 11th, were the failures before Lunar 9 was a success. So they'd had 10 goes at landing on the moon before they got one to work. Now, that says a couple of things. And one, it certainly shows that their funding regime was entirely different than the current funding regime, because we would have got to 1.5 before the plug was pulled. They managed to just keep going indefinitely. It also says that it is hard. It also says that really it's probably a very good idea to think things through much more carefully before you start, so that you're less likely to fail. And that's where systems engineering and things like that become apparent. Of course, the US followed up this only 3 years later. You know, they followed this up. This was probably more like 5 years later. But this is Apollo 17 with a rover on the moon. You can imagine the rate of progress between that first soft landing in '66 and over here in the very early 70s, people walking around on the moon. What a fantastic step forward that was in time. Something that we haven't really continued the same pace, though we have made more and more progress. So soft landing is one thing, but the message on soft landing is actually quite a difficult thing to do. It's an expensive thing to do, so perhaps we can do something else. Oh yes, I'll just throw that in, just in case any of you feel, I don't know if you can just see it, but afterwards if you want the evidence and you worry about whether we ever did go to the moon, or the Americans did, these are the footprints of the astronauts walking from a lunar base to a scientific instrument bay, and taken from a recent orbiting mission. So we've now got photographic evidence. Now I expect there'll be people who think that's all been faked. Anyway, never mind. So what we were looking for in this is really another way. Okay. Now, what are the ways that we have? Well, the top left there, that was the Galileo probe into the atmosphere of Jupiter. Okay, that's interesting. That sort of thing is very interesting. You've got a nice thick atmosphere. So Jupiter, Saturn, perhaps Uranus and Neptune, okay. After that, it's not so good, but it's Venus maybe. The middle was the soft lander, that was Viking, soft lander back in the 70s. Over here we have rovers, a variant on the soft lander, but you can, it's like an augmentation of that, where you can drive around the surface. I think the first rover of any sort was probably on the moon, Lunar on the moon. But these rovers, the one up the top here is the Mir rover currently operating on Mars in its 8th year. Its original expected lifetime was less than a year, a lot less than a year. And it's still going strong. Its sister, who's over there, see I'm already personifying it, the sister over there got stuck in the sand a short while ago, but is still functioning. A remarkable piece of technology. Down here is the rover of the future. It's ExoMars. It will fly in a number of years' time, and it will, 2018-ish, and the bit on the top of the pole there is currently being built at my laboratory, so we're involved in that planetary exploration thing. These things take quite a long time to get right. So I'm not against these sorts of technology, but there's a place for all different things. And so rovers are great, but sometimes you want to dispense with the complexity of a soft landing and just come in, just land, just get in there, okay? And drop out of orbit and get onto the surface. Now, this on the left here, this is it's actually not its impression, but it's called L-Cross. It was a mission, quite a recent mission to the moon. The thing at the front was its Apogee boost motor flying in. That made an enormous bang on the surface of the moon, and then the spacecraft flew through the cloud of debris, analysing it as it went over the next, seconds, perhaps a minute or so, as it went through the cloud of debris, and then itself impacted on the surface. And while it was analysing, it transmitted back to Earth, and it detected, for instance, water ice on the surface of the moon, which is a very interesting observation, quite unexpected, but very profound discovery that in the poles of the moon there is water ice that's been there for billions of years. A very interesting thing if you want to explore. So what we would like to be able to do is get there cheaply. If you can get there cheaply, perhaps you can get to multiple sites. And we would also like to get below the surface, because the surface of all these objects has been in sunshine on and off for a long time. It's been affected by micrometeorites. And if you really want to get to grips with what's going on in the past, then get below the surface. One interesting thing about the moon, for instance, if you can go to the moon, is that if you want to know what the Earth was like 3 billion years ago, go and stand on the moon, because that hasn't really changed much in 3 billion years, where the Earth has completely turned over. Now, an impact. Now, of course, we could hit the moon, things like the moon earlier on. That was Lunar 2, see, another Russian program. That was before the last one, of course. 59, that was. That was pretty good. That was at their 6th attempt. They hit the moon on their 6th attempt, which is pretty good going. They managed to get in the middle of the moon at the front. First impact of an object on any man-made object and an object outside the Earth. But we're interested here in an alternative approach. And so this is where the high speed. So we thought, and this isn't a new idea, but we wanted to take it the next step. We were looking at technologies which have been around for a while, and some applications to planetary exploration have been considered. And these technologies, you can probably guess a little bit from the colour of the vehicle up there where this technology is getting deployed at the moment. I'm not ashamed of that. So, and the company, the name here, this picture down below it, we were allowed permission to show this, but I'm not allowed to tell you what this thing is that's travelling through this. It's just come out of 3 meters of reinforced concrete. It's come out the other side. And we were talking to the technologists there. We weren't particularly interested in what they were putting inside these objects. We wanted to put some instrumentation inside them. But we were sort of saying, well, how is it going to survive, etc. And he did warn us that it would probably get scratched during the experience. And that was actually a quote, that they will get scratched, he said. Now, so what we wanted to do, and this was where the technology comes in, what we wanted to do was convince the world that, I'll convince British UK government as well, that such a technology was credible, that it is possible to land on the moon, or an object like the moon, at a velocity of about 350 meters per second, which is 600 or 700 miles an hour. So sort of speed of sound sort of speed. That's very fast, right? That's a very fast impact. And not just to impact, but then to actually function during the impact and go on afterwards to perform scientific measurements of a variety of sorts. And we stuffed them full of interesting technologies. And we carefully packed those technologies and adjusted those technologies so that they would survive the impact. And amongst the technologies were things like magnetometers, radiation sensors, elements of a mass spectrometer, elements of a seismometer. Now, seismometer there will be looking for moonquakes. And these elements, not the full seismometer, but the sensitive bit, which is what we've flown, a very fine silicon wafer, had to survive the impact and then go on to, in his case, but would go on to measure vibrations equivalent to a mouse walking across the back of the theatre here. It would be, very sensitive, yet have to survive something really very dramatic. We built a microprocessor and all that sort of thing, gathered data. We had accelerometers which were working during the impact. So we built 3 of these, different payloads in each one, and we took them on to Pendine to trial them. Now, just before I go on and talk about those trials and what we did, just to give you a backdrop of where we were at that point in time. So we were trying to establish credibility for a technology. These are the missions that have flown before. The Japanese had a Lunar A program. They built a couple of penetrators for that, did some tests on them, but the program was cancelled when it ran out of money, basically. And it had run on for years and years, and finally it was cancelled. Mars 96 were 2 very low-velocity Russian penetrators, which were launched but failed to reach Earth orbit, so they didn't make it to Mars. So Lunar A and Mars 96, nice technologies, but never got beyond the atmosphere of the Earth. And then DS2 were 2 very small penetrators, about the size of this bottle of water, that sort of size, which were deployed onto Mars and never seen again. My theory is they had a bag thrown over them by the Martians, because they do that all the time. Almost everything we put on Mars disappears, including the soft lander that was flying with DS2 also disappeared, so we don't happen to that. Actually, in practice, it was quite a immature technology that they flew. So there'd been a bit of a track record, but the message we were getting across was, don't forget, there have been people dropping these things out of aeroplanes since the 40s. Some people really do understand what it takes to survive an impact. And if you talk to the right people, you can get it right first time. So this was what we did. It's about that big, okay? One of these things. You'll see me holding it in a minute. It's about that big, painted blue so we can photograph it, and striped so we can see whether it spins or not. It's strapped to a sled on this, and you can see here an image of it with a rocket motor behind it. So it's got this collection of what is about 8 rocket motors behind it, and then the sledge, and then it's going off down this track at Pendine in South Wales, and in the distance there's an enormous box of sand. of cold compressed sand. And it's going to accelerate down that track. It will take about a second to accelerate up to 600 miles an hour. It's about 700 in actual this instant. And then it will take about 2/1000th of a second to stop when it gets to the sand. We chose dry sand because that's the nearest thing, two reasons really. One is it was the nearest thing we have to lunar regolith. And the second thing is we are on a beach and it's much cheaper than choosing something else. Okay, so we chose dry sand, actually a good thing. Inside the penetrator, you can see on the top right side there, you can see the payload. The payload is this sort of modular stack which slides inside so that means that we can test everything independently. Each of those payload elements consists of a particular experiment, and you can see on the right there the one that had the seismometer elements in it. We had perhaps about 20 of these elements in each one, a microprocessor, etc. on board. And they get on. Now I'm going to show you the video now. I have to play a little bit here. About there, I think. So this is, we've been waiting all day for this. It should just happen in a moment. Now, you'll see it again from behind in a minute. The thing that went into the bucket at the bottom here wasn't the penetrator. It was the sled underneath the penetrator. You can see this penetrator is sitting here waiting to go, and what you see mostly is smoke here, but you get the idea. This track's about a mile long, and of course we're not allowed to stand anywhere near it. We're in a bunker miles away. We flew one of those on each day of the week for 3 days, the interesting thing, I'll just show it, this is in slow motion now. You see it flying across here in slow motion and impacting. Its nose is a bit high, which was a disappointment. We didn't want its nose as high up as, but we couldn't get that down. There's one of the rocket motors on its way to Swansea. We never did find it again. We were told that if it did miss the sandbox, it would land in Swansea. They didn't tell me how often that happened. So there's some still photographs of it going in. You see it's released from its situation. It's got this flared tail, notice, and it's quite a nice picture of it going in, and it's just about to say goodbye. And it went about 4 meters into the sand before it stopped in this big sandbox. The poster lasted throughout we were very proud of the poster. It's a very, very well designed poster that survived. You see it ripple in the picture. So that was it afterwards. We can confirm that it did indeed get scratched. You can see the scratches on the side. It's basically been sandblasted at 600 miles an hour for about 2 or 3 milliseconds. The tail got a bit bent, but we expected that from the start. But actually, remarkably, its basic shape was unchanged. The only damage to it of any significance is the tail at the end, and that's there for atmospheric reasons, and just to try and keep it stable in the atmosphere as it goes those 20 yards to the target. And we wouldn't have that in an actual flight. So that worked all right. We had a bit of trouble getting the tail off. You can see me making some final adjustments towards getting the tail off at the end. That didn't work at all, and we eventually got the guy with the Black & Decker to saw it off. We'd had enough and we wanted to go home, frankly, so we cut the end off. And then we downloaded the data. As you can see, we downloaded the microprocessor. We found that the forces were more or less what we expected in the first trial. The impact, it suffered a force of what we measure it in G, so 10,000 G. When you stand up, you're in a 1 G environment. This was about a 10,000 G environment. So that means that if you were standing with those sorts of forces, you would feel that you weighed about 1,000 tons. That's big. So your knees aren't going to take it at 1,000 tons, okay? So we are in a very different sort of circumstance here. That's why people were so skeptical of whether or not this could be done. But it can be done, and the way it's done, and the way the Kinetic have shown us and people have shown us before, is the most important thing is to prevent motion of things. So everything is encapsulated in solid epoxy and things like that. And then you can just prevent motion, and then you can rely on the models produced by your mechanical engineers, etc., which will tell you whether things will exceed their ultimate strength. And if you design it so it won't exceed that, then it's going to survive. And that's what we did. And of all those experiments, almost all of them worked faultlessly. There's the only 1 or 2, we had a washer come off something and things like that. But basically, all the, everything worked. And for 3 trials, the microprocessor worked flawlessly throughout the trials. We had connectors working and everything. This was the actual seismometer. You can see in the seismometer trace, the first cut is where it's released from its sledge on the left there. It has a little bit of force at that. Then there's the main impact, and then it travels through the sand, and it just happened in this particular one, it hit the back of the box effectively, and it had a bit of a nudge at the back. But that was fine. Now you can see me there holding it, so you get an idea. You see I'm holding it quite carefully, right? That's not because I could possibly damage it by dropping it. It's just that it's quite heavy and it would go straight through my feet. So I could drop that on a car park and it wouldn't matter to the machine. It's just designed to last, Anyway, we had a great time. So the message there, I think, the message about the penetrator, at that time, this was, I think, is there a pre-financial collapse term? I don't know what the word is, but pre that time, we were anticipating a large sum of money from government to put 1 of the, or 4 of these things on the moon. That has now gone on hold while we try to sort out other things. The other nations have become interested. Before that time, there were no nations who were actually really working on penetrators, with a little bit of Japanese work tailing off. Now there are programs in China, there's a program in Canada, and the European Space Agency is funding a program with us on future missions. Now these are the 4 targets of penetrators in the future. There's the moon, is still a very interesting object. These, you obviously recognise Ganymede and Europa here, 2 of the moons of Jupiter. Ganymede exceptionally interesting because, Europa, well, Ganymede's interesting, but Europa's exceptionally interesting in as much as it has an ocean just below the surface, a planet-sized ocean, the size of the Pacific sort of thing, just below the surface. It would be and of course the water would be about, room temperature-ish. And so that would be very interesting. And Mars is another object which is very interesting for life as well. So this is the penetrator that we've designed for a European mission. Here we would impact ice. Now you imagine sand and ice aren't quite the same if you've ever tried to get an ice cube out of the fridge. And so the forces then are going to be a bit higher. We're going to be looking at 50,000 G rather than 15,000 G. So another factor of a few, it's okay, we'll manage that. And we can see that this is the design of the penetrator and its descent motor to the surface. So really that's all I'm going to say about that. I mean, the technology has come on very well. It's an example, I think, where you can be bold and you can think out of the box and say, what about one of those? But the only way you're going to convince anybody is to demonstrate it. So that's what we're going to do. Now I'm just going to finish, this is the last slide I sometimes show, just that people sometimes ask me, is there likely to be life anywhere in the universe? This is an image, this is the Hubble Deep Field. If you look at this, the original image, it's taken with the Hubble Space Telescope. This is a field much smaller than the size of the moon in the sky. Every object apart from that bright thing in the middle in that field is a galaxy. Every object's in a galaxy. The universe is full of galaxies, just stuffed full of unnamed galaxies, millions upon millions of them. And if you go and sit near, if you expanded any one of those little dots, and there's 10,000 in that picture alone, you'd see something looking like that. So there's plenty of opportunity for life out in the universe, and I'm sure it's out there somewhere. Whether any of it's watching us, I don't know. Anyway, thank you very much.
Thank you very much. I think we have a few moments for questions. Yes.
Just shout a question there.
Yes, there's a mic.
Okay. Lenny Street, can you hear us?
Yeah, I can hear you. Go ahead. Yeah.
Lenny Street from MSc Conservation course. I'm very interested in the penetrator. I'm very interested in a mission to Europa. But you said just under the ice. Obviously, you're a professor. I'm just a master's student. But just under the ice, as I understand, there's a lane is 5 to 12 kilometres.
Yeah. Well, there's a debate. It's kilometres. It's not inches. We wouldn't get to the ice. We wouldn't get to the water with this. But there's clear evidence of transfer of material from the ocean to the surface. If you look at the Europa, you see that it's covered in lines and cracks, and people believe that there is transfer, upwelling of material, and it's that material that came from the ocean that may preserve some of the chemistry of possible life in the ocean. The sort of techniques to get into the ocean, I think, are another generation away. People have some suggestions for that, melting through 5 kilometres of ice, but that's not what we're trying to do here. We'll be lucky to get a metre into the ice.
Because that's where we will capture humanity, because that is the best chance of finding life actually in the solar system, is in the so-called oceans of Europa.
Probably, well, I don't know how to do the bit. I mean, actually it might be Mars, but it's a very interesting place to go if you are looking for life. There might be some remnant of life left on Mars, and we probably get there first. But Mars is sort of a dead world now, and so the oceans of Europa could have a thriving, organic or whatever community. Yeah.
Thank you. Anybody else? Yes.
I was just wondering, if you're penetrating into the surface, what do you do about communication? I mean, contrary to the Mars rover and things like that, where you're on the surface, are there any challenges associated with getting this data back to Earth?
It's an issue, but it's not an overwhelming difficulty. You're not that far below the surface, so it depends a little bit on what the type of overlaying, but you can transmit through a few metres of sand. You need an orbiting spacecraft to relay the information to you. And the biggest problem actually is power, because you're below the surface, you're out of sunlight, and so you're going to be running on batteries. The proposal would have had one of these things working for about a year under the surface of the moon, just powered by a few kilograms of lithium batteries. That's the trick. But there is enough power in that to do the transmission. Through ice, it's a little bit more tricky, but it's doable.
Thank you. There's another question here.
Just shout.
Thanks. Would another opportunity for these extremely compact and robust vehicles be to do away with very expensive traditional rocket launchers and obviously the military connection there? You could use ultra-high velocity cannons or railguns or that sort of technology to get them.
It's an interesting concept. I haven't thought it through. Certainly, one of the original motivations for developing the technology was that they could instrument shells fired from guns, because they suffer similar sorts of forces coming out of the shell. But you can't put something in orbit from a gun on the ground. We haven't got the technology for that. And in a way, that's not really the problem. The problem is not getting up to speed. The problem is you've got too much speed while you're there. You still have to lose some velocity even to come in at 300, because the escape velocity of the moon is 2 kilometers a second. So you don't want to come in at that speed. But what you don't want to do is all that fancy business about landing and deciding when. You just want to go straight in and stuff it, Woof.
Any other questions? Yes, there's one here.
How do scientists find the correct location on moon or wherever to land? How do you assess?
How do we decide where to land?
Yes, exactly.
There would be a whole committee set up to do that, but and it would take years because they would never agree with each other. But there were some fundamental things. There are some places on the moon which you really want to go to. One place is in the shady craters at the poles, where the sun never shines. The sun hasn't shone there for 3 billion years. And so that's where this water ice is, a very interesting thing to do. And then you really want somewhere fairly flat, so you can measure that with not too many buried rocks, and you can measure that from radar from orbit. And you want to put these seismometers well spaced. So, it's not difficult to find locations. Actually, Europa is a bit more tricky. There are a few places on Europa which are suitable, but not an enormous number, because Europa is very rough. It's a very, very rugged object, whereas the moon's fairly flat. But no, there is no shortage of spaces, but I think it is going to be a challenge to get anyone to agree which ones. That's always an issue.
Yeah. Any others?
Hi. I was wondering, in terms of tracking, how are you going to, is there a radar type system or LiDAR, or how are you going to track it down to wherever you want to land?
Okay. The way that the landing sequence is, it's in orbit originally. It's in orbit. So in order to land, it has to lose its orbital velocity. So it has a motor on the back. And the motor sort of faces in the direction that you're travelling and stops the penetrator in its tracks. So it flies across, stops, and then falls. And this, what's called the descent motor, is then detached. But it would probably have a camera on board. So you would watch it down. And the camera would give you enough fidelity to very accurately determine where it landed. Of course, it's then a transmitter, so you can determine from its emissions again where it's landed. The descent motor will actually impact somewhere else on the moon, somewhere out of the way. It's a bit of a challenge to make sure it doesn't hit the back of the penetrator. You have to make sure it doesn't. But so it's not too difficult to work out where it's been. One could imagine sort of Ranger-like photographs of the moon getting bigger and bigger as the thing works down towards it.
There's one more here.
Do you think these penetrators will have better performance than surface penetrating radars?
I think it's horses for courses, really. The sorts of things this penetrator will be able to do you can't really do any other way, because it will be intimately connected below the surface. But something like a penetrating radar from orbit will study a very large area, where the penetrator will study the area only a few meters in diameter. So you'll get a very good view of a local circumstance, whereas anything from orbit will give you a planetary-wide but not quite such a good view. Both of them are necessary. I don't think penetrators replace anything. They're a complementary. They complement the existing portfolio of technologies.
Thank you. I think we have time for one more.
Hi, could you tell me who does the convincing to get the government to pay up for these projects?
Well, yeah, well, it's a sort of shared endeavour, really. It starts with people like me, but then you have to convince people who run space agencies, and they have to convince ministers, and ministers have to convince somebody who knows nothing at all about any of this, called the Chancellor Exchequer. So it's a sort of a layered thing, and there's many other factors. What's the economic return to the country about the technology? Can it be used elsewhere? So I think that the thing that was working really well was that it was exciting. It was not a new technology. It was successful, and those things were working really well. But at the moment, it's hard to convince. Now, you've seen what it's like. It's hard to convince people to stop raising tuition fees, let alone anything else. So I can give you their names if that helps. And if you can work on it, I'd be grateful. Yeah.
Well, thank you very much indeed. Now, I hope you'll all join me in thanking Professor Smith.